Okay, so now let's start to use the results of the derivation of the electrostatics of a p-n junction. So perhaps the most important quantity that we can solve for is the actual depletion width. So the depletion width is the region over which we're assuming that n and p are actually 0. So the charge density is only given by nd plus and na minus. So this here is the depletion approximation that sort of underpins this simplifying of the p-n junction. Now our built-in voltage, you could measure it from either side. And in fact, I should mention that because it results from an actual charge density in space, the vacuum level also manifests the same amount of built-in voltage too. Just like if you put static electric charges in a vacuum, voltage potential will develop. Okay, so the expression for the total depletion width, after you go through and solve those three equations that we just laid out, is that the depletion width is the square root of 2 times epsilon relative, epsilon naught, the quantity here, V built-in minus V applied, and then all of this over Q, and then ND over NA. So when I've written here the expression for the depletion width, I've added a term here that corresponds to applying an external voltage. And the sense of that external voltage is such that if you apply a forward bias, a positive number for VA, V applied, you actually sort of undo the built-in voltage. You work against it. So we can imagine clamping a hand on the p-type side and then lifting the n-type side with this voltage. And what will happen actually is you're sort of grabbing a hold of the Fermi level on this side and actually causing them to change relative to each other. So that's the action of an applied external voltage. On the other hand, if you grab hold of the p-type side and you apply a reverse bias, meaning V reverse is VA less than 0, we would be working to reinforce the built-in voltage and make the band bending bigger. So in reverse bias, the depletion width will actually have to expand, and the reason is it has to give more voltage, which means higher electric fields and wider depletion widths to encompass more charge on both sides. So again, the depletion width will shrink for voltages greater than 0 and get larger for reverse bias or applied voltage less than 0. So now let's look at the consequence of the fact that we have a situation where we have a conductive material here separated by a dielectric insulator here with another conductive material here. We can model this almost like a parallel plate capacitor, and thus the junction has some capacitance and can be used to give capacitance in circuits. So now let's take a look at the capacitance inside a PN junction. So I've drawn here a real space picture of our junction. We have free carriers on both sides giving electrical conductivity to these two regions. And because the N naught is the same as ND for full ionization, we call this region here the quasi-neutral region on the N-type side. And similarly, we have a quasi-neutral region, or QNR, on the P-type side. Then we have our depletion width in the middle. Now we said that if we apply a reverse bias, what's going to happen is that the boundaries of the depletion width on both sides are going to move out slightly such that they sweep out a little more charge. They make the depletion width bigger. So if this is our WD naught, this is our WD of V reverse. And they'll sweep out this extra bit of charge. Now, let's imagine that we applied a sinusoidal voltage so that the boundary of the depletion width is sweeping back and forth, just oscillating between these two positions. So what's happening really is that we're moving free charges, in and out of these two regions right here. And that turns out to be physically equivalent to a parallel plate capacitor that we're applying the same voltage across. So that capacitor has a width given by WD. It has some cross-sectional area going into the board. And then it has a dielectric constant, epsilon relative, epsilon naught inside. So we can express the capacitance of such a parallel plate capacitor simply as epsilon relative, epsilon naught times the area divided by the distance between the plates, which is WD. And now we're going to denote that this is a function of voltage. So typically, for one-dimensional device work, we'll move the area over here, and we'll write our capacitance in farads per centimeter squared. So it's quite a simple expression. Now, what this allows us to do is to actually adjust the capacitance in a circuit on the fly by applying a voltage to a PN junction, to a diode. So one function of a PN junction in circuit design would be for a varactor, or a variable reactive load capacitance. So now let's look at a simplifying case. The general PN junction with arbitrary doping on both sides is what we've been talking about so far. But let's talk specifically about a P plus N diode, which we would call it one of these one-sided diodes. So in this case, our NA is much, much greater than ND. And so we take our expression for the depletion width, and it reduces down by cancellation of assuming that NA is much bigger than ND, allows us to cancel the numerator and denominator in the original expression and end up with 2 times epsilon relative, epsilon naught over. So if we pop this into the expression for capacitance, we get our depletion width capacitance equal to square root of. What we can do then now is recall that if the doping on the the doping on the p-type side is much greater than on the n-type side, then the depletion width is is given approximately by Wn. That means that the p-type depletion width is so small. And if we have that situation, what we can do is actually a technique called capacitance voltage profiling, or CV profiling. So what we're going to do is measure the capacitance as a function of voltage. And so what we're going to do, here's our x equals 0, and here's our WD, which is we're saying is approximately equal to Wn. Here's our P plus side. Here's our N side. As we apply reverse bias, we can move the depletion width further and further into the material. And as we move it the other way, the forward bias, we move it closer to the junction. And at all times, we can measure the capacitance. And from that, because the only variable that's unknown in here is the doping on the n-type side, we can actually use it to measure that doping. So if we want to get a plot which is linearly proportional to voltage, we're going to have to square this and invert it. So we take 1 over c squared, and this equals twice v built in minus v over q epsilon relative epsilon naught and d. So if we make a plot then of 1 over c squared versus voltage here, we're going to get data. So the reverse bias is going this way. The forward bias is going this way. And I just realized I drew my line with the wrong slope with that convention. So really, we're going to get the reverse bias. We'll have a higher 1 over c squared because the capacitance will actually get smaller. And we'll get some data over some range here. We may not be able to actually touch. We may not be able to touch this axis, but the intercept is clearly given by the built-in voltage, and then the slope is given by this collection of terms here. The slope would be all these. So this nice compact expression can actually let us determine the doping on the lightly doped side of a p-n junction. And actually the same technique works for Schottky junctions also, where you're using, instead of a p plus layer, let's imagine you're using a metal which formed a built-in voltage into the n-type doped material also. So you can do CV profiling on either case. Okay, so within this topic of CV profiling, let me mention two more effects. So one is interface trapped charge or fixed charge. So here's our p-n junction, and let's imagine now that we made it by depositing a P plus layer on top of an n-type wafer. And when we did that, somehow we trapped some impurities or other defects at this interface. And we're going to have a sheet charge, a charge per area fixed at that position where the metallurgical junction occurred. And let's give it a negative charge. So compared to this case where we have our our WD on the P side and our WD on the N side, adding up to the total depletion width. Now what's going to have to happen is some extra positive charges are going to have to be added to maintain that charge balance. And so our depletion width on the N-type side is going to have to get a little bit bigger. Or the depletion width on the P-type side will have to get a little bit smaller. And that's just to maintain the overall charge balance. So what this means is that the presence of interface charges can show up in the CV profiles, and it takes a little more interpretation to figure out whether they're there, but it does allow you to measure their presence and even their density per unit area. The last thing is if you, let's say, have a one-sided junction where your doping is a function of x, it's not a constant value. And this procedure here can be generalized. Instead of just sort of making a strict linear plot of 1 over c squared versus voltage, what we can do is generalize that slope to be a derivative. So we can take the slope ddv of 1 over c squared versus voltage. And this is going to be equal to 2, sorry, there's a negative 2 there, q epsilon relative epsilon naught and d of x. So our instantaneous slope, or our slope at any point along that line, can be related to the carrier density at that point. So you may see curvature to a plot of 1 over c squared versus voltage. And the local slope gives us the local ND at the depletion width given by the applied voltage at that point. So let's imagine that we have this P plus N junction. We apply some reverse bias, and our instantaneous depletion width at some applied voltage is here. We're actually measuring ND of this depletion width at that applied voltage from the local slope at that point. So this can be used to profile through non-uniform dopant densities, especially those produced by diffusion or ion implantation into the semiconductor. So that concludes our discussion of the pure electrostatics of p-n junctions. We've looked at how the carrier density on both sides induced by the doping leads to a built-in voltage. Then we've come up with a set of 3 equations that link the built-in voltage to the depletion widths. And we've introduced the concept of treating the p-n junction like a parallel plate capacitor to determine the junction capacitance, and then talked about how that can be used to actually measure doping as a function of distance through CV profiling. So in the next sections, we'll talk about currents starting to flow in junctions. And first, we'll deal with breakdown and reverse bias, and then we'll talk about the currents which are introduced into the depletion width by minority carrier injection, leading to the ideal diode equation.